Okay, class, this is a recap of 1-3, locating points using ratios. This is our second day on it. Quick note, you had an IXL homework for this, IXL code J42. Just need to work up to a score of 60. Around 75 or 80, it changes question types a little bit, but if you just work to 60, you'll be fine for now. Let's talk about just a quick recap. We have talked about this. We talked about section formula for points on a number line, where we had to identify things like n and x1 and m and x2, which was all perfectly fine as long as we knew that we were starting at C and knew to call C x1, and we were ending at D and knew to call that x2, and we were given the ratio of m and n. We could just use this formula here every single time if you want. The quick example, we could just recap this. We could say this is a -5, and we could say this is a location of 7. And we want to split this in a ratio of choosing something large and arbitrary. Your ratio is not necessarily simplified all the time. In a ratio of 10 to 14 as our m and n. We'll find out where p is. All we'd have to do is take our numbers of x1, x2, m, and n, plug them into our formula to get a coordinate for us. We'd go 14 times -5 plus 10 times 7 all over 10 plus 14. We get -70 plus 70 over 24, or just 0 over 24, or just 0, telling us our point P has a location of 0 on the number line. We saw this, but we really wanted to extend this into much more interesting problem-solving situations. So, keeping this idea in mind, we're going to think about this problem here. Jorge is traveling 2,563 miles from New York to San Francisco by car. He's going to stop for gas when the distance he has traveled to the distance he still has to travel is 2 to 5. We want to know how far Jorge traveled the next time he stops for gas. So he's starting in New York, traveling to San Francisco. That's a good thing to note. If we know we're starting in New York, let's label that x1. If we know we're ending in San Francisco, label that x2. When we're trying to partition this, we're looking for 2 sort of line segments compared to 5 remaining line segments. I don't want to count stops necessarily. I want to count line segments. We can sort of count it here. We want to have, we can see going from New York to San Francisco, there are 6 gas stations, but there are 7 line segments. There's 1, 2, 3, 4, 5, 6, 7 times he's going to have to start and drive the car. We want to know where he's going to stop, so he's traveled basically 2 of those parts and has 5 remaining. You guys at class did pretty well. You identified, when I labeled these A, B, C, D, E, and F, a handful of you identified, oh, we're going to be stopping at E, because that would be 2 segments, 2 line segments over here, and 5 segments over here. That's good. That's the ratio of 2 to 5. But to go further than that, we wanted to know actually how many miles we wanted to travel. How far is it to, it looks like, Chicago? How many miles will he have traveled when he's made it to E? And, well, it's pretty easy to adjust this problem when we don't have a number line. Over here, we had a number line. Here, we don't currently have one. But, say you're going on a long trip like this, you're probably going to reset your trip meter in your car. If I'm starting in New York and I'm traveling, if I've just started, I've traveled 0 miles. So I would say my x1 is 0. If I've made it to San Francisco by the end of this trip, he will have traveled the entire distance. He will have traveled 2,563 miles. From here to here, we've got x1, we've got x2, we have our values of m and n. 2 is m, n is 5. We can just plug those in. We can plug those into our formula. 5 times our starting point of 0 plus 2 times our ending location divided by 5 plus 2, or 2 plus 5, or 7. Well, this simplifies a fair amount. It really just looks like 2 over 7 times 2,563. Pulling up a calculator for that. 2,563 times 2/7. We get a location of, he's traveled 732.3, we'll round it, 0.3 miles. This approach we've done is our normal section formula approach. This was using our section formula. But, you know, I kind of want to make it a little bit more intuitive. So I've got another method for you to see as well. We're going to look at another method that will be a slight bit more intuitive. So, the other method we're going to do for this is called our partial distance method here. All that we've just done here, that's our using the formula here. We went and identified m as 2, n as 5, x1 as 0, and x2 as 2,563. And just used our formula n times x1 plus m times x2 over m plus n. This other method that I want to show is a little bit more intuitive. It's called partial distances, or at least I call it partial distances. And the way to think about it is, instead of trying to memorize the formula, we're going to worry about the distance we want to travel. And we're going to think about the fraction we want to travel of that. So, we identified we wanted to stop here at E. We saw like we had 2 parts here that we traveled and 5 parts remaining. We're going to think about it as what fraction of the entire trip we're going to travel to begin with. We're going to travel as a fraction 2/7 of the entire trip. 2/7 times the distance we're traveling. We're traveling a total distance from x1 to x2 of 2,563 miles. And this will give us, let's see, let's just make comments here. This is going to be a fraction times the total distance but if we just dealt with that, it's important to know where we're starting. Say we didn't reset our odometer, we might see that x1 was 100 and that San Francisco was 2,663. If we didn't reset our odometer, we'd want to know what our odometer would read when we need to stop for gas. We need to know where we're starting. Just as in our normal formula, we need to know where we're starting. We need to know we're starting at x1. We need to know the same thing here. So we're going to have a starting location, or a starting point, that we're going to add on to our fraction times our total distance. So in this case, 0, because our starting point was 0. To see this a little just more formally, I wrote it on the board for you guys. We said our starting point was whatever we called x1. Our fraction that we're going to travel was the ratio, or was a fraction. It was m over m plus n. And then the distance we were going to travel was going to be the distance between x2 and x1. If I want the distance between two things, I'm going to find the distance by subtracting. I'm going to find the difference between two things. As a small note, this value here, x2 minus x1, this can be negative. Your x1 could also be negative. So point that out here as well. x1 could also be negative. These are things that we'd have to concern ourselves with on a normal number line here. We'll take a look at one more sort of example, and we'll sort of approach it with the partial distances formula approach instead. Our last question here is, Kendrick is on a zip line, and he's riding 1,800 meters. The zip line's 1,800 meters long, and it's starting 600 meters high above the ground. After he jumps, someone's going to take his picture. We want to know when the picture is taken, the distance he has traveled to the distance he has remaining is 1 to 2. So we got a ratio there. That's important. And we want to know whether he's going to be in the picture. There's some box where the picture will be framed, where he'll be able to either be in the picture frame or he won't. The question is, will he be in the frame? To do it, we're going to have to do a little bit of graphing here. It helps to draw a picture. So on the page here, we're going to create a little bit of a graph here. We're going to create an X and Y axes. We've got our x-axis. We've got our y-axis. We'll number things a little quickly. So we've got 1, 2, 3, 4, 5, 6. Call that 600 feet, or 600 meters. Call this 100, and call this 200, 300. Just marking a couple because I feel it's a good thing to have a couple points marked. And I'm not going to count along here just yet. because I probably don't have enough actual space along the number line here. I'll do, let's see, 2, 4, 6, 8, 10, 12. I really don't have enough space, especially if we need to travel 1,800 meters. So I'm going to go and just connect it to this point here. I'm going to connect my 600 to this point here. Now the first challenge in this is that the question asks you to think about something else. And I ask you to think about something else here. The zip line is 1,800 meters. Not horizontally, but diagonally, it's 1,800 meters. This is 1,800 meters. So first real thing we need to do is find, where's this ending point? Where is it? We know its height is going to be 0, but we don't know its y value, or its x value, excuse me. To do this, we're going to have to use Pythagorean theorem, because we see we have a right triangle. We have a height, or we have a hypotenuse here. C equals 1,800 meters. And we have a height for this triangle, we'll call it side B, of 600 meters. We saw this recently. A squared plus B squared equals C squared. We're going to plug in 1,800, 600, and find out what the distance along the number line will be. The distance along the x-axis will be. If you take the time to work it out, squaring 1,800, squaring 600, moving all the terms to one side to get a squared by itself, and then square rooting both sides, a will give you a value of 1,697.1 is what we said. So that means we got 1,697.1 down here. That's a lot of work that we've done here, but it was necessary work because now we know where we are ending on the zip line and where we're starting on the zip line. The approach we just saw for partial distances or for section formula was one-dimensional. Now we're going to be applying it two-dimensionally. The easy thing is that when we do it two-dimensionally, we just have to do it once for the x's and once for the y's. We do the process once for the x's, once for the y's. So we'll do that. Going to my second page here, we'll do this partial distance approach. For x. If we're doing partial distance, as a reminder, it's always going to be starting point plus the fraction times the total distance. Our formula for that, again, looks like x1 plus m over m plus n. We're just converting our ratio of 1 to 2 into a fraction times the total distance. The total distance is x2 minus x1. This will give us some x value that we care about. Well, let's see. M and N are 1 and 2. We're sort of splitting our picture up into 3 parts. We've got a first part we're going to have traveled, and then we're going to have 2 parts remaining. That's just a way to help you sort of think about it. This is comparing the starting part to the ending part. So we need to sort of break this into like 3 spots, into 3 line segments, and we're aiming for like a spot around here. We're going to hopefully find what that coordinate is, because we only have traveled 1 compared to 2 of them. We'll find out where that is with the x's, then we'll do the same thing with the y's. X coordinate wise, he's starting at 0. He's starting all the way to the left in the picture. He's starting at an x value of 0. Then we're going to be adding a fraction of 1 over 3 of 1/3 times the total distance he's traveling horizontally. Now he's traveling to 1,697.1 from 0. 1,697.1 minus 0. Or much more simply, 1/3 of 1,697.1. We're just evaluating that. This numerically gives us a value of 565, we'll say 0.7, rounding it to 1 decimal place. So that means the x-coordinate for this point that I put down here is 565.7. We're going to repeat the same process for the y's. A little bit faster now. Our y's, we're going to need to know the starting y value. We're going to need to know the ratio m over m plus n. Notice the ratio is going to stay the same from the x's to the y's. And then we need to know the distance between the y values. y2 minus y1. Our starting height was 600. So we're going to have 600 meters there. Plus this fraction is going to be the same as our 1/3 from earlier, times our ending location, or final height, is 0. We're ending at the bottom. So we're going to have 0 minus 600. And this is something I warned you about. The distance here could be negative. The distance here could end up being negative. So we've got 1/3 of negative 600 that we're going to add 600 to. Well, that's 600 minus 200 in the end, or 400 altogether. So the height that Kendrick is going to be at on this zip line is a height of 400. So 565.7, comma 400. I tried to end the problem early by putting some parentheses. We've got a coordinate here. Last thing is just see if he's in the picture. The picture is going to show from 400 meters to 1200 meters. Let's say that's roughly here to here. Is he in that horizontally? Yes, he's in 565. And it's going to show from ground level to 500 meters high. Is he under this height here? Yes, he is. He's in this box. Kendrick's going to be in the picture frame. You had, as a reminder, in IXL related to this take the time to check out the video on that IXL if you want more practice. It is an important IXL for you to practice. There are multiple methods to approaching it. You could use the partial distance formula, or you could just use the section formula as well. Either method works. Good work.